Hello, this is Ashish and I'm going to demonstrate the code artifact for my research, demand prediction in a bike sharing system using machine learning techniques. The data for this research has been obtained from the Metro bike share system established in Los Angeles, US, which consists of more than 5 million records for the year of 2019, and the station detailed dataset has also been used for the research. The data has been stored in the Google Drive and to be accessed by the Google Colab. The first process, that is the data transformation process, is the most important process since the original data does not contain any prediction feature. This is the original data files, and as can be seen, there is no prediction features, but the start time and the end time has been used to derive those features. The transformation process is structured in multiple functions which facilitates and creates the desired data. The whole process gives the following output as it can be seen here. The transform data is the data which contains both the docs and the bikes demand, and the time interval is basically the interval for which the demands were generated. Like it can be seen here, the interval is 30 minutes, and similarly for this research we have used two intervals that are 30 minutes and 60 minutes, and the third is the graph weights, which is utilized by the graph when the graph data structure is being created. The first model implemented is the ARIMA model. As it can be seen here, it utilizes the transform data and prepare it for it to be executed. However, there is a condition for using ARIMA, that is the data should be stationary and Dickey-Fuller test and rolling stats are performed. If the p-value is less than 0.5, then the data is stationary, otherwise a differentiation needs to be performed. PDQ parameters are obtained by iterating it over a range of values, and the results obtained are evaluated using the MSE, MAE and root mean square error. The prediction is shown here in this graph. It can be seen that the actual bikes demand is varying. However, the ARIMA model has predicted just a straight line, which is not accurately able to learn the variation. To determine the docs demand, the process is repeated again. The same stationary test is performed, and the results can be seen here. Like the results are also the same for the docs demand. It created a straight line instead of varying curve. The second model implemented is the LSTM model. It utilizes the Keras package. The data preparation process is the same as used in ARIMA model, which works on single station data at a time. The data has been split into 80-20 ratio, for 80 for training, 20 for testing, and the data has been scaled using min-max scaler for it to be normalized, standardized. The model consists of 4 layers of LSTM, and it's compiled over a range of over hyperparameters like Adam optimization, mean squared error as loss function, epoch size is 30, batch size is 32. Early stopping function has been utilized for the epochs to stop early if the val loss is not decreasing further, and the training loss and the validation loss chart has been made here. It can be seen that validation loss is more, however, than the training loss, which means the model is not accurately able to predict the actual demands. The values are evaluated over the same parameters, that are MSE, MAE and RMSE values. The values obtained are comparatively lower than the ARIMA model, and the prediction chart is made here. Unlike the ARIMA, which just plotted a straight line, variations can be observed, which is a good thing. And like as you can see, for the high variation, a high peak is generated. However, the learning curve is really slow, and the same process is done for the docs prediction, and over the same parameters, same evaluation tests are performed, and here the same result is obtained. That is, the model is learning, but the learning curve is really slow. The third model is the SGCN model. This model is adopted to test the second assumption, that is whether the spatial properties, that is the neighboring station, affects the prediction of a particular station. To implement this, the PyTorch package has been used, and these versions are utilized. The specific version needs to be downloaded before implementing it. First of all, the graph GCN convolutional network works on graph data. The graph data has been created using PyTorch underscore geometric library. A graph data is basically panda arrays converted into multi-dimensional tensors, and the sample size here refers to the 400 small graphs created of the whole network, and time bound refers to the time IDs created in the first data transformation process. The GCN model for both the TAC GCN and SGCN is same, except the spatial convolution layer, which is GCN convolution for the SGCN model, whereas for the TAC convolution it is TAC con. These layers are predefined, and the model has been referenced from multiple sources. The parameters are defined, and the results are obtained over the model is trained over 4 epochs, because any more epochs halted the process, because the too much RAM is consumed in training the model. The MSE loss is varying, which means the model is not properly able to learn the variation in the data, and the final prediction results can be seen like the results are pretty good. Like it can be seen like with the increase in demand, the prediction is also increasing. However, with too much high variation, the model is not accurately able to learn the process. And one other thing in this model is that for the LSTM model and RMA model, the codes need to be implemented twice. However, for this model, in the single runtime, it produces prediction for both the desired features. The process for TAC convolution is also the same. However, the result obtained for TAC convolution are not pretty good, because as you can see, the learning curve is really low for both the bikes and docs demand.